The image comes through in pieces, the way they always do. First, a grid of red shifted light resolving, pixel by pixel on a screen at the Space Telescope Science Institute. Someone is measuring a redshift. The number keeps climbing, and with it, the age of what they are looking at keeps falling. And at a certain point in that calculation, several astronomers in that room go quiet, because the object in front of them is a galaxy, fully formed, glowing with the light of old, established stars, sitting at a point in cosmic history when, by every working model available in 2022, nothing like it should exist. Yet, this is the story of the Big Bang's earliest, strangest headache, and it starts here, in early 2023, with the James Webb Space Telescope staring at galaxies that are, by the numbers, too big, too bright, and too early. So, was this a confirmation of what we already believed about the universe, or a warning that something in the model is wrong? Those two words, confirmation and warning, sound almost interchangeable, and they are not. The entire story you are about to hear lies in the gap between them. Here is the thesis. The standard picture of how galaxies form after the Big Bang says they should start small and grow slowly through mergers over hundreds of millions of years. JWST found galaxies that skipped the slow part. That does not mean the Big Bang did not happen. It means there is a real, published, ongoing argument among cosmologists about whether our model of how fast structure can form in the early universe is missing something, and the honest version of that argument is a lot stranger and more interesting than the headlines let on. The comfortable version of this story, the one that ran in early 2023, said James Webb had discovered galaxies that broke cosmology. Massive, fully grown galaxies present just a few 100 million years after the beginning of everything, at a stage when the universe was supposed to still be assembling its first small clumps of stars. The real version, buried in the actual paper by Ivo Lab and colleagues, published in Nature in 2023, is more careful. It described a small population of red, candidate massive galaxies, seen as they were roughly 600 million years after the Big Bang, with estimated stellar masses on the order of 10 billion suns. Candidate. Estimated. Those words are doing a lot of quiet work. Read that again, because it matters. A candidate galaxy is not a confirmed one. Early distance and mass estimates from this kind of infrared imaging carry real uncertainty, and the authors knew it. The comfortable version, says James Webb, proved the impossible galaxies were real. The real version is that some of them were not. A follow-up study led by Pablo Arrabal Haro, published in Nature later in 2023, went back with spectroscopy, a more precise way of measuring both distance and composition, and found a split result. Some of the extreme, ultra-early candidates held up. Others turned out to be much closer, much more modest galaxies, or in a few cases, compact regions glowing from a feeding black hole, mimicking the signature of an ancient, massive galaxy. The field's own title for that paper was blunt about it, calling it a confirmation and a refutation in the same breath. The comfortable version treats this as one big, singular discovery. The real version is a slow accumulation of separate, independent warning signs, stretching back further than most people realize. Long before Webb launched, astronomers using the Hubble Space Telescope had already flagged something odd about the number and size of the earliest galaxies they could detect, a pattern that researchers like Fulvio Melia were describing as an unusual early galaxy problem as far back as the 2010s. Then, once Webb came online in 2022, that trickle became a flood. Rowan Naidu and colleagues flagged early bright candidates. Emma Curtis Lake and her team spectroscopically confirmed several galaxies sitting less than 500 million years after the Big Bang. Then came direct spectroscopic confirmation of GNZ11, a galaxy first spotted by Hubble years earlier, now shown by Adam Bunker's team using Webb's NIRSPEC instrument. That near-infrared spectrograph, capable of splitting a galaxy's light into a detailed fingerprint, to be sitting at a staggering 430 million years after the beginning of the universe, and showing chemical signatures of a surprisingly mature, evolved system. Each of these was, on its own, a strange result. Together, they were a trend. To understand why that trend is a problem, you need one plain picture. Think about building a city. Standard cosmology says galaxies grow the way cities grow, from small settlements, gradually merging and expanding over centuries, gaining population and infrastructure step by step. Nobody expects a fully developed metropolis, with its own established districts and history, to appear in a spot that was empty countryside a generation earlier. That is roughly what the early CDM model, the standard cosmological framework, built on cold, dark matter and a cosmological constant, predicts for galaxy growth. Small halos of dark matter form first, gas falls in, stars ignite gradually, and mass builds up slowly, limited by how much raw material, how many baryons, ordinary atomic matter, is even available. What Webb found, in its most extreme cases, looked less like a growing settlement, and more like a finished metropolis, appearing where the foundations had barely been poured. One of these results is a curiosity. 2 is a coincidence. 3 is a pattern. Alongside the mass problem, astronomers noticed the early galaxies were unexpectedly compact, an order of magnitude smaller in physical size than models predicted, packing their stars into unusually dense structures. Then came the discovery, by teams including Sandro Takela and Christina Williams, of galaxies that appeared quenched, meaning they had already stopped forming new stars at absurdly young cosmic ages, which requires not just fast growth, but fast shutdown. An entire life cycle compressed into a sliver of cosmic time. Mass, size, and life cycle. 3 separate lines of unexpected data, all pointing the same direction, toward galaxies that matured faster than the standard clock allows. There is a second, independent pillar of evidence worth knowing, because it did not come from galaxy imaging at all. In 2023, Michael Boylan-Kolchin ran the numbers on the most extreme of the lab candidates and found that some of them, if their masses held up, would require converting an implausibly large fraction, in some calculations, approaching the entire available supply of ordinary matter inside their dark matter halos directly into stars. Essentially, no waste, no inefficiency, a conversion rate physics does not normally allow. That is a completely separate kind of argument, built from halo statistics and known cosmic baryon budgets, rather than pixels on a telescope image. And it arrived at the same uncomfortable place as the imaging data. 2 independent methods, pointing at the same tension, is exactly the kind of overlap that makes scientists sit up, step back from the telescopes for a second, and think about what any of this has to do with you. Every atom in your body was forged inside a star. The calcium in your bones, the iron in your blood, the carbon in every cell, all of it traces back through generations of stellar life and death, all the way to those first galaxies. If the early universe built its first generations of stars faster and more efficiently than we assumed, then the entire chemical assembly line that eventually produced you started running sooner than textbooks currently say. This is not an abstract argument about redshift numbers. It is a question about how quickly the universe became capable of making something like a human being. None of this is a story about scientists hiding something. It is a story about translation, a hedged academic sentence describing a population of candidate galaxies in tension with baryon conversion, limits under standard star formation assumptions, does not survive contact with the press release deadline. Journals and universities have real incentives to lead with the boldest, defensible framing, because that framing gets covered, gets funded, and gets read. Editors compress nuance. None of that is dishonest. The original papers, with all their careful qualifiers, are sitting on public preprint servers for anyone to go read in full. This is not saying the Big Bang is in doubt, and it is not saying the last century of cosmological evidence, from the cosmic microwave background to the abundance of light elements to the large-scale structure of the universe, has been wiped out by a handful of galaxies. the foundational evidence for the standard model remains overwhelming. What is genuinely unresolved is narrower and more interesting. Whether the earliest generations of galaxies formed stars in unusually short, intense bursts that make them look brighter and more massive than they really are. Whether the stars themselves were different, more efficient at producing light per unit of mass, or whether galaxy formation in the first few 100 million years runs on physics that current models underestimate. Later surveys, including a systematic study published through the FRESCO program, found that most massive early galaxies actually fit existing models reasonably well once realistic uncertainties are included, and that only the most extreme outliers still demand something unusual. The pattern has not vanished, it has narrowed. So picture that room again. The astronomers watching a number climb on a screen, the redshift ticking upward while the age of the object in front of them ticks down toward numbers that used to sound like typos. What they were looking at was never a broken universe. It was a universe that had, somewhere in its first few 100 million years, learned to build things faster than we had given it credit for.